So we're going to look at 7.2 absolute value functions. And before we start discussing it, I just want to go over the graph that you have in front of you. The blue part is your absolute value function. It's the graph of y is equal to the absolute value of x. Okay, and the red part, which actually extends above the x-axis, because this part of the graph is really blue on red. Okay, so it actually does extend above the x-axis. This is y equals x. Okay, so the vertex is right here. It's at 0, 0. So our vertex divides the graph of this absolute value function, y equals absolute value of x, into two distinct pieces. One part is the part that goes up to the right, and the other part is the part that goes up to the left. An absolute value function is a function that involves the absolute value of a variable. So in this case, the absolute value of x. Okay, so the following explanation is for absolute value functions. Okay, so for all values of x less than 0, okay, so that means everything to the left of the origin, the y value is negative x. Okay, so what that means is that this part of the graph is y equals negative x. For all values of x greater than or equal to 0, so that means from the origin and up to the right, the y value is x. So that means that this part of the graph is y is equal to x. Since the function is defined by two different rules for each interval in the domain, you can define y equals absolute value of x as the piecewise function. Okay, and we're talking about y is equal to, and then we use this parentheses, x if x is greater than or equal to 0, and y is equal to negative x if x is less than 0. Okay, so this is a piecewise function. Okay, and what it means is, if you go to the right of the screen, a function composed of two or more separate functions or pieces, each with its own specific domain, that combine to define the overall function. Okay, so we have two pieces here. We have one where y is equal to x. Its domain is that x is greater than or equal to 0. And the second piece is y is equal to negative x if x is less than 0. Okay, so you can see that our absolute value function is made up of two separate functions, y equals x and y equals negative x. Okay, now I'll just read this explanation and then we'll go back up to the graph. The graph shows how y equals the absolute value of x is related to the graph of y equals x. Since the absolute value cannot be negative, okay, and we mean the absolute value of x, the part of the graph of y equals x that is below the x-axis is reflected in the x-axis to become the line y is equal to negative x in the interval x is less than 0. Okay, so we go back up to the graph. Okay, and because the absolute value of x can't be negative, the part of y equals x which is below the x-axis gets reflected above the x-axis. So this part of the line is going to reflect over the x-axis. Okay, so we'll just make a note of that. Reflect over the x-axis. Okay, and if we use our vertex as our center point, right, then the part that gets reflected over the x-axis is where x is less than 0. Okay, remember, everything to the left of 0 means that x is a negative number, so less than 0. Okay, the part of the graph of y equals x that is on or above the x-axis is 0 or positive and remains unchanged as the line y equals x in the interval of x is greater than or equal to 0. Okay, so that means that this part of the graph, y equals x, is true when x is greater than or equal to 0. Okay, and y equals negative x for your absolute value is true for when x is less than 0. Okay, so you can see this is where your piecewise function comes in. All right, here and here. Okay, so example 1, graph an absolute value function of the form y equals the absolute value of ax plus b. We are going to take a look at the absolute value function y is equal to the absolute value of x minus 3. The related function is y is equal to x minus 3. And we are going to graph both. Okay, and we're going to start with y equals x minus 3. So we'll get the y and x intercept of that. All right, so x-intercept, remember, happens at y equals 0. We will substitute in 0 for y. Solve for x, and we find x is 3, so our x-intercept is at 3 and 0. Y-intercept happens when x is equal to 0, so substitute in 0 for x, solve for y, and you get that y is equal to negative 3, so our y-intercept is at 0 and negative 3. Okay, so we're going to plot those on the graph and graph them. So x-intercept, 3 and 0, y-intercept, 0, negative 3. We're going to use a dotted line because the function that we really want to graph is the absolute value function. And so y equals x minus 3. Okay, now our absolute value function is, and if we compare it to the one that we looked at earlier, which y is equal to the absolute value of x, okay? So whatever x is, the absolute value of that number is always going to be positive, which means that y is always going to be positive. That means the negative part of this graph is going to be reflected above the x-axis where all the values for y are positive, okay? So that means we want to take our y-intercept and we want to reflect at the same number of points above the x-axis that it is below. And it's below by 3, so we are going to reflect it up by 3. Okay, and it will take on the same shape as the bottom part of this graph. We're going to use a solid line to graph it in because this is the function that we want to graph. And so that is the y is equal to the absolute value of x minus 3. So the x-intercept of our original function is the x-intercept of the absolute value function. So you can see that right here. Okay, same x-intercept. Since the point did not move, okay, in other words, it's the point 3, 0 is part of the graph y equals x minus 3 as well as the absolute value of x minus 3. We call it an invariant point. An invariant point is a point that remains unchanged when a transformation is applied to it. So if you go to the right, what other points on the graph are invariant points? Well, any part of the graph that didn't change. Okay, so that would be this arm, the right-hand side arm, the part that is already above the x-axis. Now, we've already said that our x-intercept is an invariant point. So we want to pick those points which are greater than that, right? Because when we go right on the graph, that means we're getting values larger than 3. And so where are the other ones? Where x is greater than 3. Okay, another question, or actually something that I'd like you to notice. Note that the graph of y equals the absolute value of x minus 3 is also like y equals the absolute value of x. And what that means is they have the same shape. Okay, so if I graph in y equals absolute value of x, we would get this graph. Okay, so it has exactly the same shape. Okay, but it's shifted 3 units left from here, or if you like, the graph of y equals x minus 3 is shifted 3 units to the right from the absolute value of x. Y equals the absolute value of x. Okay, so another way to explain that, if you take a look at the vertex form of a function, y equals a f of x minus p plus q, where the vertex is p and q, and we take a look at our absolute value function, y equals the absolute value of x minus 3, I can put plus 0 for my plus q. That gives me a value of 3 for p and 0 for q, so my vertex is at 3, 0. Okay, we know that already. Let's take our y equals absolute value of x function, write it in the same form, so we're going to put in 0 for p and 0 for q, and the vertex is at 0, 0. So you can see that this vertex 3, 0 is shifted 3 units to the right from this vertex. Okay? So it's another way that you can graph it. If you could graph in y equals the absolute value of x, and you know that this graph is a shift of 3 units to the right, then you can just shift everything over by 3 units, okay, from the y equals absolute value of x over to y equals the absolute value of x minus 3. All right, let's take a look at domain and range of our linear function and our absolute value function. Now, for all linear functions, the domain is all reals, and our range is all reals. Okay? And that's because for a linear function, one part of the graph will go into infinity into the negative direction, and one will go off into infinity in the positive direction, so that would give us a domain and a range of all reals. Our absolute value function is a little different. We would treat it the same way that we would treat a quadratic function. So the domain for that would be the same as a quadratic function. Okay, and why is that? Well, because an absolute value function looks a little bit like it, right? It's got straight lines, but it has a vertex. It has 2 arms that go up. This particular one is opening up, and so we could apply the same rationale. And so the domain for this is all reals. All right, and the range is also similar to a quadratic function. We want to take a look at the vertex. Our smallest value for y, our lowest value for y, is at 0. Every other point on the graph is greater than 0, and so y is greater than and equal to 0. Okay, so the next thing that we want to do is to express this function as a piecewise function. Okay, so that means we want to break it up into 2 different functions that will represent our absolute value function. And so we're going to write y equals, and we put in a large parentheses. Okay, and we start with our linear function, which is x minus 3. And then we write if, and then we go back up to the graph and figure out which part of the absolute value function that is. Okay, so for this particular function, it would be this arm. Okay, and if you take a look, everything to the right of the x-intercept or the vertex would satisfy this part of the graph. Okay, so everything to the right would be our domain because we're looking at values which are greater than 3, and so we say if x is greater than or equal to 3. Now, the second part of our function is going to be the negative of our absolute value, of our linear function, okay? And we can gather that from the definition for our absolute value function where y is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. Okay, so we just take the negative value of this function for our second part of our piecewise function, and we go if. Then we go back up to the graph, we take a look at it, and we look to see which part of the graph is going to be the negative part, and that is the other arm. Okay, this is the part which is negative bracket x minus 3 bracket. Okay, and notice that with respect to the x-intercept, those points would be to the left of that. Okay, so that means less than the 3. Okay, and so we go x is less than 3. Okay, now another way that you can work this out, you can go x minus 3 is greater than or equal to 0, solve for x, and then you can see that that would give you this. And then you can go x minus 3 is less than 0, and so x is less than 3, and that would give you this. Okay, now if you're not sure that this branch is y equals negative x minus 3, we can work it out. Okay, we know that the y-intercept is at 3, so b is 3. We know the slope is up 1 and to the left 1, so that would be negative 1 over 1, or if you like, 1 over negative 1, which is negative 1. So when we plug that into y equals mx plus b, we get y equals negative x plus 3. Now, to make it look like this, we just have to factor out a negative 1. Okay, and that would make this x minus 3, and so you can see there the same. Okay, all right, so that's the end of this part. Okay, so example 2, we're going to now graph an absolute value function of the form f of x equals x squared plus bx plus c. That means we want the absolute value of a quadratic. Okay, so we're going to take a look at the absolute value function of f of x equals x squared minus 4. The related function is y equals x squared minus 4. So we're going to get our x-intercepts and vertex of y equals x squared minus 4. Alright, so let's start with the vertex because that's fairly basic. Alright, remember we have this in the form of y equals a times x minus p squared plus q. Okay, and if we put this in that form, we're going to get y equals a is 1, so we don't have to worry about that. And then x minus 0 squared minus 4. And so we have a vertex which is at 0 and negative 4. Okay, recall x-intercepts occur when y is equal to 0, so we're going to plug in 0 for y. We are going to solve for x, so we're going to move the negative 4 over. We get 4 equals x squared. Square root both sides, and don't forget to put plus and minus 2. Okay, so we're going to sketch this graph in. our vertex is at 0 and negative 4. We have x-intercepts at 2 and negative 2. And because this is not our absolute value graph, we are going to sketch in the parabola with a dotted line. So this is y is equal to x squared minus 4. Okay, so we're going to use this graph to graph y equals the absolute value of x squared minus 4. Okay, and since there are no negative y's in y is equal to x squared minus 4, you will flip the negative part of the parabola, okay, over the x-axis. Okay, so which part is negative? Well, that is any part which is below the x-axis. We want to flip that over the x-axis. So that means we want to take our vertex, which is at 0 and negative 4, and we want to move it the same number of units above the x-axis. So that's going to take us to 0 and 4. Okay, we keep our x-intercepts. We're going to keep the part of the graph which is above the x-axis. Okay, so all we're doing is flipping the part that's below above. So we will draw that in now because this is the graph that we want. Okay, remember a nice curved line because this is a parabola, and then a nice curved line here, curved line here, and so you get this blue graph, which is y is equal to the absolute value of x squared minus 4. Okay, so let's take a look at invariant points here. Okay, in other words, which points did not move? Okay, well, our x-intercepts didn't move, so x equals 2 and x equals negative 2. And then everything which is to the right of 2, so greater than 2, and everything which is to the left of negative 2, so that means less than negative 2. Okay, and you can combine these. By writing x is greater than and equal to 2 and x is less than or equal to negative 2. Okay, so that's where your invariant points are. Now if you take a look, we're going to compare domain and range, okay, for these functions. So of our original parabola, okay, that was the one that I drew in green, all right, our domain is all reals. Why don't I do this in green? All right, and our range, okay, well that's everything above where y is equal to negative 4, so we say y is greater than or equal to negative 4. All right, and then let's do the domain and range for our absolute value function. We'll do that in blue. Okay, now if you take a look at the graph, you have all values for x which are less than 0, and you have all values for x which are greater than 0, because the graph is going to move off to the right and off to the left, okay, and everything in between here also. All right, so the domain then is going to be all reals. And your range, well, take a look at what the bottom part of your graph is. Okay, the bottom of the blue graph. What's the lowest points, or the lowest point? Well, it's going to be where x-intercepts are, right? So at 2 and 0, and at negative 2 and 0. So what's our y value at that point? 0. So our range is going to be y is greater than or equal to 0. Okay, so now we're going to write our piecewise function. All right, we're going to keep in mind that by definition we get this. All right, so we're going to say, all right, y equals our original function, our quadratic is x squared minus 4. Okay, and now we want to write in our domain restriction, right? So if, so we go back up to our graph and we say, okay, well, which part of the graph is the original x squared minus 4? Okay, well, the original x minus 4 is along here and along here. Okay, so where is our domain for that? Well, everything to the right of 2 and everything to the left of negative 2. So when we write the domain for the part of our graph which is y equals x squared minus 4, we want everything to the right of 2 and everything to the left of negative 2. Okay, so how do we write that? Well, we say that x is less than or equal to negative 2, or x is greater than or equal to 2. Okay, so the second half of our piecewise function is the negative form of this. So we go minus and then in a bracket x squared minus 4. Okay, now what is the domain restriction for that? Well, we go back up to the graph and we say, okay, well, that is this part of the graph, right? Okay, and where's our domain for that? Well, everything in between negative 2 and 2. Okay, so we say everything in between. So we remember what we did at the beginning of the year. We put the smallest value first, less than, put the variable we're considering in the middle, which is x, and then less than, and 2. So that means all x values between negative 2 and 2. We don't want to put less than and equal to, because we've already put the equal to symbols on our first piecewise function. Okay? All right, and so we're done. So our last example for this section, 7.2, example 3, we want to graph y equals the absolute value of x squared minus 6x plus 5. So once again, a quadratic. And we are going to start by taking a look at its related function, which is y equals x squared minus 6x plus 5. Okay, so we're going to start by getting the x and y intercepts. Now, to get the x-intercepts, we're going to use y equals x squared minus 6x plus 5. We want to solve that, so we want to, oh yeah, and remember, x-intercepts happen when y equals 0, so we're going to plug in 0 for y. And now you can see this looks like a quadratic equation that we can solve, so we're going to factor. Alright, so what factors of 5 give us 6, 5, and 1, as long as they are both negative, and so we can see that x is equal to 5 and x equals 1. Alright, to get our y-intercept, we are going to use, so this is our x-intercept. Our y-intercept, we are going to use the absolute value function. Okay, so y is equal to the absolute value of x squared minus 6x plus 5. And recall that y-intercepts happen when x equals 0, so we're going to substitute in 0 for x. And we get the absolute value of 5, which is 5. Okay, so we have x-intercepts, one at x is 5, so 5 and 0, and one at x is 1, which is 1 and 0, and we have a y-intercept at 5, which is 0 and 5. Alright, so now let's get our vertex. Now you can get the vertex by completing the square, or you can use the vertex formula. We're going to use the vertex formula because it'll be a little easier. Alright, so from our original function we can see that b is negative 6 and a is equal to 1. And so we're going to plug in negative 6 for negative b and 1 for a. And when we simplify this, we get 6 over 2, which is 3. Okay, and to get our y coordinate for our vertex, we want to plug that into our quadratic function. So we're going to go 3 squared minus 6 times 3 plus 5. Do the math and you get that y is negative 4, so our vertex is at 3 and negative 4. Okay, so let's go to the graph. 3 and negative 4. Okay, so let's sketch our parabola in. Now we want to get one more point because we got 4 right now, we want 5. Now because our axis of symmetry goes down through the vertex, we can take this point and we can use symmetry to plot it right here, okay, which is at 6 and 5. Okay, and so our original function then is right here. Okay, so now we can graph in our absolute value function. So we're going to keep the part of the graph which is above the x-axis. Okay, and I'll draw this in red. So the part that's above the x-axis is right here, so we keep that. And right here, so we keep that. But the part that's below, we want to reflect over the x-axis. So take a look, your vertex is 4 units below the x-axis. We're going to graph it 4 units above, right here. And then nice curve, and a nice curve. Okay, and you get this red graph here, which is y equals the absolute value of x squared minus 6x plus 5. And remember the blue one is y is equal to x squared minus 6x plus 5. Okay, so our red graph is our absolute value graph. Now our invariant points. Okay, invariant points. Okay, so what part of the graph is exactly the same? All right, well, everything to the right of where x is 5, so x is greater than or equal to 5. And everything to the left of 1, so x is less than or equal to 1. Okay, that's where all of your invariant points are. All right, let's take a look at our domain and range for both functions. Okay, so for the blue parabola, that's our original related function. Okay, the domain is all reals, and our range, if you take a look, our bottommost point is where y is negative 4, so everything above that, so y is greater than or equal to negative 4. And if we take a look at our absolute value function, okay, the domain will be all reals. Okay, and the range, if you take a look, your lowest values for y are 0 again, so y has to be greater than or equal to 0. Okay, and now let's write in our piecewise function. Okay, we go y equals. All right, and remember, we're going to use this as our model. Okay, and so our related function, x squared minus 6x plus 5, and then the negative version of that. Okay, and then if, and if. Okay, and so now we take a look at our domain. Okay, all right, so the original part of our graph. Okay, that means the part that is y equals x squared minus 6x plus 5. Okay, that part. Everything to the right of 5. Okay, so everything which is greater than or equal to 5, and everything to the left of 1, so everything which is less than or equal to 1 is part of our domain. Okay, so where x is less than or equal to 1, or x is greater than or equal to 5. All right, and then we take a look at the part which is our absolute value. That's this one here. And that's everything in between 1 and 5. Okay, everything in between 1 and 5. So we go smallest number first, less than variable that we're considering x, less than 5. Remember, we don't have to put equals into here because we've already included it up in here. Okay, and that concludes our lesson.